Hey guys, it's Miss Johnson, and I'm here to bring you our first piece of Section 3.2. I mentioned when we started Chapter 3 that Section 3.2 is a really hefty section. There's a lot going on in this section, so we actually have it broken apart into 4 different pieces. So just hang tight with me, gear up, buckle up, and we'll get through all of this together. So this is just our first piece of Section 3.2. You can see that there's even 2 pages in this section. So we're just kicking off of learning targets because there are so many learning targets in the first piece. Today we are talking about least squares regression. We're talking about how to make a regression line for a data set when we have a scatter plot. So it ties directly into our scatter plot, and how do we make a prediction line for those values. So a regression line is a linear relationship or straight line that is between 2 quantitative variables. The regression line summarizes the relationship between 2 variables, but only in a specific setting, when one variable helps explain the other. So when there's an association between 2 variables, we can draw a best fit line, or in other words, a regression line through that data set, just like you see in the picture here. So in this picture, we've got all our data points in red. All these data points on the graph, you can see them all plotted there. This blue line that goes through the middle, this is the regression line. And this is, and actually I shouldn't have drawn an arrow on that, because it doesn't continue on, it only goes to the end of the data set. So anyways, there's your regression line. Your regression line goes through your data set, and it is our best fitting line. It's the line that gives you the best prediction of what could happen within this range of data. You get an equation to that line, and that equation is similar to slope-intercept form, except that your slope, or your y-intercept, is typically written first. So you can see that normally we would say mx plus b. You can see that the y-intercept is what is listed first, and then the slope times x is listed second. That's just how they write it in statistics. But it's the same format. It doesn't really make a difference mathematically. All we did was switch the addition. So the regression line is a line that describes how the response variable y changes as the explanatory variable x changes. Regression lines are expressed in the form of y hat. That's literally pronounced y hat is equal to b sub 0 plus b sub 1 times x. So we have a b value that is our y-intercept, and then they also call your slope b1, basically. And this is going to give us a predicted value for a given value of x. It gets tricky and confusing, and this is something that people forget quite a bit. But what I want you to remember is, you just put this in your head right now. Predictions, where hats. Okay, so this y hat is a predicted value for the data set that you're looking at. You can see that on this blue line, almost none of the data points fall directly on the blue line. Maybe this one right here, but that's really about it. Everything else is off the blue line. So the blue line isn't giving you the exact results of the data set. What it's giving you is a close prediction. So let's just talk a little bit more about what that prediction might be. So I'm going to use the example of 100,000 miles in this prediction here. It says a random sample of 16 used Ford F-150 Super Cruise was selected from among those listed for sale on autotrader.com. The data are shown in the table below. For these data, the regression equation is price hat. The hat of the price, or the predicted price, is equal to 38,257 minus 0.1629 times the miles driven. Predict the price of the Ford F-150 that has been driven 100,000 miles. So what you can see in this data set is you've got all those points on the line. This is the same graph that we were just looking at on the previous slide. So here's all your data points, all those red little dots there. Okay, and then you've got that blue regression line. This is our regression line, and this is the equation of the regression line. Okay, so with that equation, I can take 100,000 miles and I can plug it in for the number of miles driven, or in other words, my x, because that's the explanatory variable. Okay, the price is the response variable. But I can plug it in for my miles driven and I can get a price. So what that shows me is this point right here at 100,000 miles is about approximately just under $22,000. So if there was 100,000 miles on the car, on the truck, the price of the truck would be about 22,000 miles. Now, if you've ever purchased a used car or looked at cars or whatever, we know that there's a lot of other factors that go into the price of the car other than just miles driven. What's the condition of the engine? What's the condition of the aesthetics? Like, how is the exterior? Are there scratches? Are there dents? How's the interior? Are there stains? Are there rips? Things like that. Is the stereo functioning and all the electronic stuff? All of that goes into the price of the car. But miles is arguably the first thing that people will look at when they're purchasing a car, which is why you can make a regression line. But all those other variables are what make these points not fall directly on the line. They're just close to it, okay? Let's talk about extrapolation. Extrapolation is something that happens when we try to look outside of our data range. So in the previous slide, the data range went from 0 to 160,000 miles, okay? So the data went from 0 to 160,000 miles, okay? Let's talk about what the price of the car would be. It says, can we predict the price of a car with 300,000 miles driven on it? So we would take that same equation, we'd plug in 300,000 miles into the miles driven, and here's our price that we get. We get a price of negative $10,613. Now, I don't know about you, but I've never heard of a car dealership having somebody walk onto their showroom floor or walk onto their lot and say, hey, I'm going to hand you $10,000 and you get to take this car. That just doesn't happen. That doesn't make any sense. What happened here is that we have some serious extrapolation going on, okay? When we use the regression line to predict a value that's far outside of the interval of x values used to create the line, that prediction is often not accurate. And obviously we can see that that's the case in this example. So since our data that we used to create the regression line went from 0 to 160,000 miles, that was the range of our data, when you use that line to predict $300,000, that same equation, that doesn't, or 300,000 miles, that doesn't make any sense. 300,000 miles is a far, far, far way away from 160,000 miles. So that's way outside of the range of data that was used to make that equation, which means that I cannot use that equation to predict that value. It's not going to make any sense. So it says don't make your AP exam caution here is don't make predictions using values of x that are much larger or much smaller than those that actually appear in your data. So if your data is in a specific range, you cannot use that prediction line, that regression line, to predict something that's way far outside of it. That's what's called extrapolation. All right, now let's get into residuals. So how do we get this line? That's the magical question. Where does this line come from? How do we find the best fitting line and write that equation? So the equation is based on something called residuals. Residuals are the distance from any data point and the prediction line. Okay, so it says in most cases, no line will pass exactly through all the points in the scatter plot, obviously, because data is raw and messy. Because we use the line to predict y from x, the prediction errors we make are errors in y, the vertical direction in the scatter plot. So we speak in terms of y because y is what we're using to predict. X is your explanatory variable, x is always there. So we're talking about the distance away from the line in the y variable, in the vertical distance. So these vertical distances are called residuals, or in other words, the leftover variation from the response variable. So the residual is the difference between the actual value of y and the predicted value of y. Here's how you get it. Actual y minus predicted y, or in other words, y minus y hat. Because again, remember, predictions wear hats. So if I wanted to find a residual for this example, I'm using the same 16 Ford F-150s. I've got my data there. It's in two kind of pieces. Here's the first piece, here's the second piece, but this is just all 14 pieces of data. It says, calculate and interpret the residual for the truck that was driven 70,583 miles. Okay, so if we find the predicted price based on our regression line, I would take that 70,583 and I'd plug it in right there, and I'd get a predicted price, again, predicted price of 26,759. If I go into my data set, into my data table, the data that was given to me, and I look for that 70,583, it's this first point right here. The actual price is 21,994. So the predicted price was 26,759. What's the residual? I get the residual from taking the actual price minus the predicted price. In the same way that we would take the data minus the mean in a z-score formula, we'd take data minus mean over standard deviation. We do actual price minus predicted price in the residual. Okay, so the actual raw data comes first, just like it did in the z-score formula. So anyways, we take the data minus the prediction. In this case, that's 21,994 minus 26,759, and my residual is negative 4,765. And yes, it is possible to have a negative residual. It says the actual price of the truck was $4,765 less than the cost of the predicted price given by the regression line with X equaling the miles driven. This is your interpretation. Oftentimes you are asked to interpret value or interpret values. So this is how you would interpret a residual. You have to say what the actual price is, you have to say the direction, you have to say that it's the predicted price given by the regression line, and you have to give the X variable. Those are all the things that you need when you're going to interpret the residual. So then let's talk about what could have happened here. This may be a truck that has a scratch on the side, or maybe it needs new tires, or maybe there's something wrong with the engine, or maybe the radio is not working, the stereo system, audio system. Okay, so there must be some other factor going into the price of this truck that brought it way down from what the predicted line would tell us, okay? So interpreting a regression line, it says a regression line is a model for the data, much like a density curve is a model for our data in chapter 2. When we were in chapter 2 and we were looking at density curves, those density curves were not perfect. They were a loose translation of where our data fell. They didn't show every single little nook and cranny and jagged increase or decrease or peak or valley or whatever. It gave us a general curve of whatever the data looked like. Okay, that's how the regression line is. The regression line is just a model. It's just a model for the data. It doesn't contain the actual data. It's just a model. The y-intercept and the slope of the regression line describe what the model tells us about the relationship between the response variable and the explanatory variable. So in this regression equation, this guy right here, and remember that's just like slope-intercept form, b sub 0 is the y-intercept and b sub 1 is the slope, okay? And that's the amount of which the predicted value changes with each unit increase. So if we were going to look at the two pieces of the Ford F-150 example, here's our regression line. Price is equal to $38,257 minus 0.1629 times the miles driven. If I was going to interpret the slope, which is something you'll be asked to do, this is how you would write up your interpretation. The predicted price of a used Ford F-150 goes down and that's because of the subtraction, by $0.1629, or in other words, 16.29 cents, for each additional mile that the truck has been driven. So notice that they mentioned the predicted price, they mentioned direction, they put the actual slope value in there with context because it's labeled. Okay, so this is direction. They reference that they're doing the predicted price. They give you the label of the X, or in other words, they put it in context that the truck has been driven. So all those things are important for interpreting the slope. If I was going to interpret the y-intercept, I would say something along the lines of the predicted price, again, in dollars, of a used F-150 that has been driven 0 miles is that $38,257. Now, let's talk about the y-intercept. Oftentimes, the y-intercept does not actually have a whole lot of meaning to your data. It is not possible to have a used truck that is driven 0 miles. The very definition of a used vehicle is a vehicle that has been used. In order to use a vehicle, you put miles on the vehicle. So if you put miles on the vehicle, then you can't have a truck that has 0 miles on it. That's just not something that's possible. So the y-intercept doesn't often have a whole lot of context, but you will spend a lot of time interpreting the slope. The slope is something that's going to have a lot of context in your question, so that's one that you will have to write up interpretations for. So pull stars with that one. So just be careful. It says when you're asked to interpret the slope or y-intercept, it is very important to include the word predicted in your response. Otherwise, it might appear that you believe the regression equation actually gives the actual values of y. Okay, so this is important. You have to say the predicted value, and you will go from an E to a P if this were a free response question on your AP exam. If you don't have that word predicted in there. Predictions wear hats. If you are looking at a regression line, you are looking at predictions. You have to put hats on your variables, and you have to use the word predicted in your interpretations. All right, that's the end of our first piece. So thanks for making it through with me. We will carry on with part number 2 next time.